Have you ever noticed how a balloon can stick to a wall or make your hair stand up? That's electrostatics, and today we tested how electric charge actually behaves through a series of experiments. Our first experiment is called attraction and repulsion. First, we charged these balloons by rubbing fur on them. This is an example of charge transfer where electrons move from one material to another, in this case, onto the balloon. Now both balloons have a net negative charge, and when we bring them close, they repel each other. That's because of the fundamental rule, like charges repel due to electric force. When I touch the balloon, I'm grounding it, giving the extra electrons a path to leave. Now it's either neutral or less negatively charged, and when we bring them back together, it attracts to the charged balloon. That's because of induction. The neutral balloon's charges rearrange in response to the electric field. This same idea explains why clothes stick together in a dryer or why static shock happens after walking on carpet. Next, we tested how a charged balloon affects water. Water is neutral overall, but each molecule is polar, meaning it has a slightly positive and slightly negative side. When the balloon gets close, its electric field causes the molecules to rotate so that the positive side faces the balloon. Because the opposite charge is slightly closer, the attractive force is stronger than the repulsive force, so the water bends. And this is actually similar to how microwaves heat food, by making water molecules rotate using electric fields. For our next experiment, the can roller, first we charge the balloon by rubbing it with fur. This transfers electrons onto the balloon, giving it a negative charge. Then we bring the charged balloon close to the can, and the can starts rolling towards it, almost like it's chasing the balloon. What's happening is the charges inside the can shift. The electrons get pushed away from the balloon, so the side closest to the balloon becomes slightly positive. That positive side is attracted to the negative balloon, since opposites attract, so it pulls the can forward, and as the can moves, the charges keep shifting the same way. So it keeps getting pulled towards the balloon, which is why it looks like it's chasing it. Electrostatic precipitators use a similar idea, but instead of moving a can, they remove tiny particles like dust and smoke from the air in power plants. Inside the system, particles in the air are given an electric charge. Then large metal plates with the opposite charge attract those particles and pull them out of the air. So just like the balloon pulls the can by creating an electric force, the plates pull pollution particles out of the air using the same type of force. This helps reduce air pollution and makes power plants cleaner. For our next experiment, we use a Van de Graaff generator, which builds up a large amount of electric charge on the metal dome using a belt. We then bring a grounded metal sphere close to it. And grounded just means that it's connected to the earth so charge can flow in or out of it. And we use this in everyday things so that you don't get electrocuted. When the grounded sphere gets close to the charged dome, a big difference in charge builds up between the two objects. The electric field becomes strong enough to ionize the air, which lets electrons jump across the gap as a spark. The electrons are actually moving between the generator and the grounded sphere because the ground provides a path for the charges to flow. And this is basically a small-scale version of lightning where charges build up and then suddenly discharge through the air. Next, we bring out this neon tube and we put it near the Van de Graaff generator, and it starts to glow because the strong electric field is exciting the gases inside the tube. But we noticed that the brightness and how far we needed to hold it to get a reaction changed depending on the orientation of the tube. When the tube is aligned in the same direction as the electric field, the field doesn't drive charges very effectively along the full length of the tube, so the glow is weaker and we have to get a lot closer. But when we hold it perpendicular to the field, the electric field acts across the tube more strong, creating a large potential difference across it. This causes more electrons to accelerate and collide with the neon gas atoms, which increase excitation, and that produces a brighter glow. Brightness depends on how effectively the electric field can drive charge movement through the gas inside the tube. And this is the same principle behind neon signs and even natural phenomenons like the aurora. All of these experiments show that electric charge doesn't just sit still. It creates forces, fields, and energy transfer that affects the world around us. From bending water to creating sparks, electrostatics explain both simple everyday effects and powerful natural events like lightning. Understanding these interactions help us see how invisible forces shape the physical world.